Hi everyone, this video is going to be an overview regarding ionic and covalent bonding. I'm going to talk fast in the video just because I want to fit it all into a short video. So know that you can always pause, you can go back and re-watch any parts or pause it while you write down notes or anything like that. So don't panic if I'm going too fast, you can always pause the video. So talking about bonds, we talked about bonds back in the matter unit. We know that they are, the thing that holds atoms together to make compounds. But here specifically, we can see that they are a force that holds groups of atoms together. It makes them function as a unit. The biggest thing that I need you guys to get out of this right here is that they're forces. It's not like there's a magical substance or matter, between them, holding them together. It's just a force. Ionic bonds get that force from the transfer of electrons. Their opposite charges are what bond them together, or what create that force to hold them together. And then covalent compounds, they share electrons, and that desire to have that full octet as a result of the sharing, that's what drives the force to hold those things together. Ionic compounds, right here, biggest thing, always between a metal and a nonmetal. Ionic compounds, always between a metal and a nonmetal. Now, if we look at the periodic table, here I'm just going to sketch like a little outline here. Okay, there's the periodic table. Over here, we have this staircase. And if you look at any periodic table, it should have that staircase kind of bolded in. The staircase separates the metals from the nonmetals. If we look, so metals are always over here on this side to the left of the staircase. Nonmetals are always going to be over here to the right of the staircase. Ionic compounds form so that they can lose or gain electrons. We already talked about this. We just haven't put the word ionic with it. But we talked about that octet. We talked about that transferring, losing, or gaining electrons. And when that happens, the result is an ionic compound. Metals will always lose electrons to form positively charged cations. And remember, if we look at the periodic table, this column has a +1 charge, +2, and +3. And those are all the metals. Those are all the ones to the left of the staircase. Nonmetals gain electrons, therefore they form negatively charged anions. And again, -3, -2, -1. And obviously that's off a little bit because I didn't have room, but nonmetals form negative anions. Metals form positive cations. So metals, positive cations. Nonmetals, negative anions. And a way to remember that, so I say, to remember that metals are cations and that they're positive. Cats have paws. I don't know why that thing is up there. So cats, like meow, have paws. Cats have paws. Cats are positive, cations are positive. Easy peasy. All right, so here's just an example. Sodium chloride, we know sodium has 1 valence electron. Chlorine has 7 valence electrons. In order to be happy, sodium needs to get rid of that one. Chlorine wants to gain one, so sodium can give it to chlorine and they can be happy together. And here's just a visual of that. So here, this is sodium's valence electron. Chlorine has 1, 2, 3, 4, 5, 6, 7. So to complete that, this electron is going to come boop and pop right in there to bond with that. And this is the result. You can see that sodium is missing that outer shell now. This shell is no longer there because it doesn't need to be. There's no electrons there. And then sodium's electron that he gave is right there. So both of them have a full shell. Both of them are happy. Their anions are formed, and they can come together as Na1, +1, chlorine -1. When they come together, what's the result? Overall charge is 0. So the net charge on any compound, on this compound, on literally any other compound, the net charge must equal 0. That's a rule. Compounds have a charge of 0. And that's why ionic bonds work so well, because we have opposite charges coming together. So here's just some examples. I don't want you to worry yourselves with these, but up here we have magnesium and chlorine. So magnesium, we know if we look at the periodic table, has a +2 charge. Chlorine has a -1 charge. If we put those together, just like we did the sodium chloride, it's not gonna be happy because it's not gonna be neutral. I'm gonna have an extra positive charge here, right? 2 plus -1 is +1. So in order to complete that, in order to totally cancel out this positive charge, I need to add another negative chlorine. And here I have +2, -2, that's gonna equal 0 overall. And so the compound itself, when I write that out, oh, geez, it looks like MgCl2, meaning 2 chlorines for every 1 magnesium. And again, it has everything to do with those charges. We'll get more into that on Wednesday, but this is just, that preview, that getting the idea of the charges canceling out, becoming neutral to make an overall compound. Okay, so metals, the only thing I need you to get from this side is that metals, when they become an ion, they do not change their name. Lithium, whether it's neutral or has a positive charge, is called lithium. Nonmetals, however, do change their name. Notice that every single one of these changes its ending to IDE. So fluorine becomes fluoride, chlorine becomes chloride, bromide, iodide, oxide, sulfide, nitride, phosphide. Those are just the most popular ones. But any of the nonmetals, if they become an ion, if they gain electrons, they're going to change their ending to IDE every time. From this slide, the most important thing down here is this. All salts are ionic compounds. So when we talk about salt, everybody thinks of sodium chloride, table salt. But the reason why we say table salt is because, in fact, by definition, an ionic compound is a salt. A salt is any ionic compound. So just, I don't know, keep that in mind, I guess. Properties of ionic compounds, crystalline solid, just like you saw in the last one, it has a real nice fit together structure based on the alternating positive and negative ions. Melting point and boiling point high compared to covalent. So if we had a covalent one over here, it would basically be the opposite of these. So no special structure, low melting point, low boiling point, not usually conductive, and not usually soluble in water. The only word here that you might not recognize is aqueous, and aqueous just means dissolved in water. So you can make note of that. It just means dissolved in water. And we'll get more into that when we do solutions. But for now, you just need to know that ionic compounds can conduct electricity. They're soluble, meaning they dissolve. And then covalent compounds are kind of just the opposite. So here's some main points about covalent compounds. We talked a lot about ionic, and that's going to be our main focus for the first few weeks. But of course, we do have covalent compounds that share electrons. And again, it's all about getting a full octet in that. And instead of all this, you can just say outer shell. I don't know why my pen keeps doing that. That's annoying. Covalent compounds involve atoms of non-metals only. Super important. So when we're looking at that staircase on the periodic table, oh my gosh, why is it doing that? Dun, 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 dun. Okay, all of these over here, those are our non-metals. So we're going to have 2 or more of those bonded together by sharing electrons. And here the term molecule is used exclusively for covalent bonding. So we can't say that magnesium chloride or sodium chloride are molecules. We can say that they're compounds. Covalent compounds are going to be referred to as molecules. Basically, all that means is instead of the word covalent, if you see molecular, they're the same thing, synonymous, same word, synonyms. And that's basically what that last thing means, or what it's trying to tell you. So sometimes, we already talked about Lewis structures. Sometimes it's hard to see why they go together, but here's kind of just a visual for you. You can see that the 7 valence in fluorine, the 7 valence in this fluorine come together to make diatomic. They both have 8 and they're happy. And that's it. Thank you.